This is a video from section 12.3 and it's based off the lecture notes. If theta is the angle between vectors A and B, the dot product of A and B is equal to the magnitude of A times the magnitude of B times cosine theta. Theta is greater than or equal to 0 and less than or equal to pi. And I could solve for cosine theta, and when I do, I get cosine theta is the dot product of A and B divided by the magnitude of A times the magnitude of B. Now what we want to do is we want to look at the scalar projection of A onto B. And so notice how I'm highlighting A, the vector A, that's right here. And I have the vector B that's along here. And I'm going to drop a perpendicular from the tip of A down to B. That's right here. And that makes a 90-degree angle. That side makes a 90-degree angle with vector B. And we want to find the scalar projection of A onto B. And that's going to represent, in this context, that's going to represent the length of this side. Now, can that scalar projection be negative? The answer is yes, and I will explain how shortly, okay? So we want to find the scalar projection of A onto B, and it's going to be written in this way, okay, as follows. If I take the scalar projection of A onto B and I divide by the magnitude of A, I get cosine theta. So think of it as adjacent over hypotenuse is cosine theta. And I'm going to multiply both sides by the magnitude of A. And so the scalar projection of A onto B is the magnitude of A times cosine of theta. But cosine of theta is A dot B, right? The dot product of A and B divided by the magnitude of A times the magnitude of B. And if you notice, the magnitude of A's cancel, and what we have left is the scalar projection of A onto B is the dot product of A and B divided by the magnitude of B. So this is the first formula that we derive. Now, if you notice, if I draw A in this way, notice how theta is greater than pi over 2, but less than or equal to pi. And in this context, notice how I drop the perpendicular down, right? So this line here is the perpendicular, and I'm looking for this piece here highlighted in blue, right? So from the initial point of B, right, this is the vector B. This piece represents the scalar projection of A onto B, and that would be a negative number. Now, next, I want to find the projection, and it's the vector projection of A onto B. And the vector projection of A onto B is written this way. Okay, I'm going to go back to the original picture. The vector projection is literally a vector. And I'm going to highlight the vector projection in red. So it's going to start at the initial point of B. It's going to extend out this way, and it's going to stop here. And so essentially what I'm asking is, what does A look like in the direction of B? That's what we're trying to calculate. And so I calculate it this way. I take the scalar projection of A onto B, right? So I'm going to take a scalar multiple of a unit vector. So what I do is I convert B into a unit vector by dividing by the magnitude of B. So I take the component or the scalar projection of A onto B and I multiply by B divided by the magnitude of B. But remember that hard work. The scalar projection of A onto B is the dot product of A and B divided by the magnitude of B, and I'm multiplying by B divided by the magnitude of B. So a unit vector has length 1. So I needed to convert that vector B into a unit vector. And so remember that the magnitude of B times the magnitude of B is the magnitude of B squared. So when I go to simplify, I get the following. The vector projection of A onto B is the dot product of A and B divided by the magnitude of B squared. This scalar, this is a scalar, by the way, so we can't forget that. That scalar is being multiplied by B. So when you do the vector projection of A onto B, this is a vector. The scalar projection of A onto B is going to give you a scalar. Okay? Let's look at some examples. Now, in part A, suppose A is the vector -2, 3, -6, and B is the vector 5, -1, 4. And we want to find the scalar and vector projections of B onto A. And regardless, we're going to need the dot product. So the dot product of A and B is going to be -2 times 5 plus 3 times -1 plus -6 times 4. And that's -37. The magnitude of A is the square root of 4 plus 9 plus 36. So I squared -2 to get 4. I squared 3 to get 9. I squared -36 to get 36. And the square root of 4 plus 9 plus 36 is equal to the square root of 49, which is equal to 7. So the scalar projection of B onto A is the dot product of A and B divided by the magnitude of A. And if I just put all that together, I get -37 divided by 7. If I want the vector projection of B onto A, that's this piece right here, I get the dot product of A and B divided by the magnitude of A squared. This scalar is getting multiplied by A. We're projecting down onto A. So in other words, what does B look like along A? That's what we're asking ourselves. Now, we already know that the dot product of A and B is -37. And if I take the magnitude of A, that's right here, and I square it, I get 49. So I get -37 divided by 49. I'm going to take that scalar times A. But A is the vector -2, 3, -6. And then when I simplify, you can see that I get 74 over 49, -111 over 49, and 222 divided by 49. And that concludes example 1. In example 2, we have the following. Suppose vector A is 1, 1, 1, and vector B is 1, -1, 1. So we're going to do the same thing. The dot product of A and B is 1 times 1 plus 1 times -1 plus 1 times 1. But that's equal to 2. The magnitude of A is the square root of 3. All right? So the scalar projection of B onto A, that's this piece right here, is the dot product of A and B divided by the magnitude of A. And the dot product of A and B is 1. The magnitude of A is square root of 3. So we get 1 divided by the square root of 3. The vector projection of B onto A, that's this piece right here, is the dot product of A and B divided by the magnitude of A squared, that's scalar, times A. So it's a scalar multiple of A. And so we get 1/3, right? Because if I take the square root of 3 and I square it, I get 3. So I get 1/3 not divided by, times the vector 1, 1, 1. That's A. And so if I take 1/3 times 1, I get a third, and I'm going to do that to all three components. And so my final answer is the vector 1/3, 1/3, 1/3. And that's going to conclude this video for section 12.3. And again, this is based off my lecture notes, this video. Okay, thank you.